So what happened in the lossy dielectric? Okay, again I suggest you guys to watch also the lecture video by the EMT education on the week 13. Okay, they will provide a lot of information, and I believe maybe you gain a lot more knowledge if you watch more and more lecture videos, okay, from the other lecturers. So in the ideal dielectric, what is ideal dielectric? Okay, ideal dielectric have the conductivity equals to 0. Okay, so they are actually a perfect, you can say it's a perfect insulator. Okay, then in here, in this lossy dielectric, in ideal dielectric, sorry, in ideal dielectric, you have a curl of H, okay, equals to J plus d over dt. This is what we learn as, this is a displacement current density. This one is conduction current density. Then we want to expand this one, conduction current density. We will obtain this. Am I correct? And this one you can expand because you have d equals to epsilon e. Okay, so you expand and you get this. Then you do some factorization. Okay, you notice both having e, so you just factorize e out. Then you have d over dt omega epsilon e. Okay, so this term, okay, this term can be also rewritten as j omega. Okay, then we do some more simplifications. Okay, we do simplification. If you notice that in ideal dielectric, epsilon is equal to 0. Okay, so here, and sorry, sigma is equal to 0. So while sigma equals to 0, then we actually have this whole equation is equal to j omega epsilon and e. Okay, so this we treat as our equation 1. Okay, however, in real life, it is difficult to have a ideal material, right? Whether it's ideal conductor or ideal dielectric. So let we turn to case, let's say, practical dielectric. Okay, practical dielectric, the mu is not, the epsilon is not equal to 0. However, they are relatively low. Okay, because this one is showing the conductivity. So for practical dielectric, the sigma is not 0, means it is not totally 0, means it's not an ideal dielectric. However, it is small. Okay, because it is it's not a good conductor. Okay, so in this case, for example, okay, we using the same equation also, but we modify according to the practical dielectrics. So the curl of H, J plus d over dt. Okay, then instead of using our epsilon here, we will use epsilon with respect to the dielectric, practical dielectric. Let's say we use this. Okay, prime, epsilon prime. Then we do some factorization, the same as in ideal case. Okay, we factorize the e out. Okay, then we use this j omega to represent our d dt. Okay, so we came across this equation. Okay, you see there's a bit different there, because in here the epsilon is 0, here epsilon is not 0, and we make this equals to our equation 2. Okay, so if we want to compare both both ideal and practical case, okay, if you want to compare the equations, okay, if you want to compare, because both is actually curl of H, So if you want to do the comparison, j omega epsilon epsilon E for the ideal case, and then for the practical dielectrics, okay. So we take this one out, okay, the E out, so we only care about this, we just focus on these things, okay. Okay, and then we do some arrangement because this one is an ideal, so we do some arrangement. We divide all with j omega, okay, then we'll have with omega 1 plus this one, okay. Am I correct? And then if we want to factorize our epsilon prime outside, then we will have, okay, so this famous equation, okay, when you learn later on, let's say if you want to go in deep with RF and microwave field, this one is very important, okay. We call it loss tangent, okay. So this is our infamous loss tangent. So what is loss tangent? For example, if you have a FR4, okay, FR4 is a non-PCB board, okay. FR4 is non-PCB board. We call it a flame retardant, okay. So it is a dielectrics. It is a lossy dielectrics. In the practical world, okay, it's a lossy dielectrics, so it have its own loss tangent, okay. The lossy dielectric, the loss tangent for FR4 is around 0.002, okay. Sorry, it's around 0.02, okay. The loss tangent, okay. The bigger the number, the lossy the material it is, okay. So now let me see on the case of what we want to refer as the capacitors, okay. Capacitors, the ideal case, okay, we will have current, and we have our JC, the conduction current density, and we have the D. This one is actually your displacement current. And then in the case of let me see this first for simplicity. You see you have IC equals to VR. This is the Ohm's law. Then your V is actually your epsilon S over your D, okay. This one is common. And then if you want to see the practical case, okay, represent this as a resistor. This one is your conduction current density, and this one will be your displacement current density. So your current will divide into two types, okay, which is the displacement current and the conduction current. So, and this conduction current will pass through an element of a resistor, and for the conduction current passing through an element of capacitors, okay, because this is just like caseware in the parallel plate, right? So it's a capacitors. So your ID is equals to J omega CV equals to omega epsilon S over D, okay. This is for the lossy dielectric, for capacitor made by lossy dielectric, okay. So if you want to see the ratio, okay, between this IC and ID, okay, you can use capital IC or capital D as long as you understand what is this, okay. The ratio of IC and ID, okay, you take the ID, okay, and if we do some simplification, we will come, this one also can be cut, okay. Then we have sigma omega epsilon, okay. So this is actually your loss tangent. Okay. And then for you to, let's say when we have current, we have volume, we have current, we have resistance. Okay. So some of our mind we also think, what about the power loss? Okay. So power loss per unit volume, okay, we want to represent within the volume. So your power is equal to sigma E square over 2. Okay. So with that, we finish our lecture. Okay. So good day and see you soon.